Okay, so here's the height of the flagpole lab discussion. You need a diagram in your notes. We'll talk about the shadow method first. Notice I'm labeling everything. I now have the meter stick and its shadow. Because the sun is at the same angle, we can use similar triangles. Now I got this data from the video. The length of the shadow was measured to be 5.5 meters, and the length of the shadow of the meter stick was measured to be 0.85 meters. Do the math and you get about 6.47 meters. Now, how does that compare to an estimate? If you watch the video, I have the meter stick next to the flagpole. And when you see the meter stick, you can actually just imagine with your fingers and pace it up the flagpole. And you're going to get somewhere in an answer of around 6 meters. So this is pretty close to our estimate. Not bad. But what if it was cloudy? You didn't have a shadow. You could use the protractor. As you saw in the video, I hold the protractor up to my eye and I sight to the top of the pole. As I tilt the protractor, I'm tilting above the horizontal. I can now make a triangle just out of thin air. If I look at the side of the protractor, I can see the angle that I've tilted it to. I measured it to be 18 degrees. I paced off the distance to the flagpole and I got 9.7 meters. The height of my eye was 1.6 meters. I didn't get that on the video, but I typed it up in the description. Now, what are we going to do to find the height of the pole? Maybe you recognize this dotted lines as forming a right triangle with an opposite and an adjacent side. You're going to practice your trigonometry and you're going to get good at it. This is opposite over adjacent equals tangent theta. Rearrange and we can solve for the opposite side. Make sure your calculator's in degrees mode. We get 3.15 meters. But we need the height of the pole. So what do we have to do? Add in the height of the eye. So using this method, we get a height of about 4.75 meters. And that seems to be a little bit low when comparing it to the estimate. I think that the problem is with the protractor. It's really hard to measure an angle that closely when it's just me. If there's two people there, then somebody else can be reading the protractor while I hold it at the proper angle. So that's probably the biggest part of my, my error. Now, kids always ask me, what is the real height of the pole? And the truth is, we don't know. When we do this at school, we all are looking at the exact same pole. And we all try to pool our resources. Some kids get a little higher number, some kids get a little lower number. And honestly, that's the way science works. Nobody really knows the right answer. We just generally build a consensus. And then you hear things that say, well, most scientists agree. And that's what we're talking about. That's the way the scientific process works. No one's going to be able to prove with absolute certainty what the height of that pole is. Even if I called the manufacturer, the installation process could be off by a little bit. So that's one thing. Another thing you want to think about is the units. We're using meters. Notice how I drew everything, labeled everything. We're using the metric system here. Not all our problems will be in the metric system, but this is the way you want to record your work. And then that's what you submit to me. So for this lab, you're going to take a picture of the object that you're measuring and then show me some work like this. So you're going to send me 2 pictures. That should do it. And then go read my notes. You're going to enjoy them.